Okay, this is the first integral we've seen of this type over here. It's a rather strange integral. It's minus 1 to the x, and you should realize that that's problematic. For example, if you took x to be 1/2, you'd have a complex number. So what I want to do is talk about what we just derived, and what we derived was this formula here. Right, now what I'm going to do is I'm going to select a number for x that would make that equal to minus 1. And the number that you'd select for x would be equal to pi. But the truth about that is that any multiple of 2 pi added onto that would also reduce to minus 1. All right, so let me go through that. I plug it in. Again, I'm selecting the x to be pi plus 2 pi k, where k is some integer number. And you get this over here. And relatively simple, by the way. So what do you get over there? Well, it's going to be the cosine of pi. And it keeps repeating itself every 2 pi k. And that's going to be minus 1 plus I. Now the sine of pi, and it keeps repeating itself every 2 pi k, is just simply 0. So what do you get over here? Minus 1. All right, so now I know that e to the I pi plus 2 pi k is equal to minus 1. So then I raise both sides to x, and I get this over here. I change the integrand to that form over there. And the reason for that is I know how to integrate e to a power. All right, so like if you integrate e to the ax dx, that would be e to the ax over a. And that's all I'm doing. All right, so if you were to integrate that, again, we're integrating this, which is the same thing as integrating this at this point. That's going to be e to that power, and that's going to be I pi plus 2 pi k over, whoa, let's look at this thing, I pi plus 2 pi k, plus some constant of integration, by the way. Since we have a definite integral, though, we're just going to evaluate it. All right? So we're going to evaluate from 0 to 1, and drop the c out. And that's not bad to do, by the way. And if you do that, what are you going to get? Let's write this over here. You're going to get, let's see, at 1 it's going to be e to the I pi plus 2 pi k over I pi plus 2 pi k minus evaluated at 0. Well, 0, that's going to be, some number raised to 0 power, so 1. And what goes on bottom? I. And then you get pi plus 2 pi k. Again, k is some integer number. Well, I got something interesting over here again. And what do I have? I have this back. I mean, I've got it back. And what is this thing equal to? It's equal to minus 1. So what do I get over here? I get minus 1. Let's write this down. Over I. Well, same denominator. So it's minus 1, and the denominator is pi plus 2 pi k. Now, you know from Math 100, they didn't like the I in the bottom. So I'm going to multiply top and bottom by I. And what do you get there? Let's take a look at that. You're going to get minus 2i on top. On bottom, you're going to get I squared pi plus 2 pi k. I squared is minus 1, so what are you getting? 2i over pi plus 2 pi k. I'm going to clean that up a tiny little bit. This is going to be 2i on top, and on bottom, what are you going to get? Factor pi out, and you're going to get 1 plus 2k. So it's the odd multiples of pi, by the way, on bottom. So let's take a look, see how we did, and let's see if we got those answers over there. All right, so we're looking at this answer right over here. All right, they do discuss one particular solution, and that's when k is equal to 0. When k is equal to 0, what do you get? You would get 2i over, well, if k is 0, you just get a pi on the bottom, and that's listed for you right over here. Now, granted, you could do k equals 1, or any integer you want, by the way. All right, so what do you get over here? If you did 1, you would get 2i, and on bottom, what do you get? You would get 3 pi, all right? And again, any k you like, as long as k is an integer number. Thank you so much for listening.